Okay, so we're looking at Unit 1 practice exam. Let's take a look here. So first set of questions are multiple choice. Write the name or structure below. Cyclobutane is the parent name. So you draw a four-membered ring. And then from there, 1, 2, dichloro. So 1 and 2, chloros. 1, 2, dibromo. 1 and 2. Biggest thing, cyclobutane is the parent. Make sure you draw that and put the right bromines there and chlorines there. Diethylpropamine. So for this one, circle the parent chain. So it includes the nitrogen. So how many carbons with the nitrogen? 1, 2, 3. Propanamine, parent chain. There's 2 ethyls, and they're both off the nitrogen, so we say NN diethylpropanoamine. We don't use numbers with the amines, we use the N to designate what's off the nitrogen, but the longest carbon chain with the nitrogen is the parent name. Correct name here, 1-octanol. So they all have 8-member rings, except for this one, 1, 2, 3, 4, 5, 6, 7. So this one doesn't work. And then from there, it's dimethyl. So here's trimethyl. Here's diethyl. So it has to be this one. Correct chair structure. I see that the bromine and the methyl right next to it are trans, or on opposite sides. And this methyl is on the same side as the bromine. So if you look at this is the wrong, this one doesn't have the right connectivity. There's no methyl next to the bromine. Here there's a methyl next to the bromine and it's opposite sides, so this could work. But then the methyl farther away is also opposite side of the bromine, but it needs to be the same. These two, this methyl and this bromine, are right next to each other, which works, but they're on the same side, then you get opposite sides. So it's this one where the bromine's down, methyl up, methyl down. That matches this. For this one, how many hydrogens in the molecule? Again, be able to write these things out. There's 1 H here, 3 here. So 1, 4, 5, 6, 7, 8, right? So remember there's an H here. If you don't see bonds, there's hydrogens there. So there's 8 hydrogens there. What type of orbital overlap is responsible for the pi bond between the carbon and carbon molecule in the below? So carbon-carbons are a pi bond. Pi bonds are only made from 2p orbitals. Add all the lone pairs and formal charges in the molecules below. Assume all atoms have full octet. So let's do that first. Oxygen with 2 bonds, 2 lone pairs. Nitrogen, 4 bonds, show a plus charge. Oxygen, 3 bonds, has a lone pair and a plus charge. Nitrogen, 3 bonds, has a lone pair. Make sure you can do that stuff first. Draw curved arrows for the electron flow from starting materials to products. Right, so this side to this side. Where do we start our arrows at? We start at electron density, so that's the lone pair here. Also notice, this oxygen loses a lone pair. Right? So it means one of these lone pairs is being used to grab that H. How many electrons in a bond? 2. These 2 electrons are forming that new OH bond. These electrons in this NH bond are then going to the nitrogen, which gets that lone pair. The oxygen is the nucleophile. That's where the arrow started. The hydrogen is the electrophile, not the nitrogen. Just because it has a plus charge doesn't mean it has to be the electrophile. Right? It's the hydrogen that's electron deficient, not the nitrogen. So make sure you write specific atoms, not just the molecule, specific atoms. Oxygen is nucleophile, H is electrophile on the left is nucleophile, electrophile. Make sure you read the question carefully. Here it says, draw the exact conformation Newton projection A as shown. So you're going to draw it exactly like this, right? Looking down from C1 to C2. So there's 1 and 2. So this is eclipse. Both H's should be down. The bromine, a lot of people forgot this carbon. There's a carbon there. Don't lose that. Bromine's dashed, and so is the chlorine. So they're on this left-hand side. The 2 methyls are right next to each other. So this is eclipsed. Want to rotate carbon 2 clockwise. So 1 is in the front, 2 is in the back. So nothing changes with 1. It should just stay the same the whole time. Rotate 60 degrees. This goes, chlorine goes here, methyl goes here, H goes here. So go from eclipsed to staggered. Right? Nothing changed with carbon 1. Carbon 2 is rotating. Rotate carbon 2 clockwise. Okay. Rotate it again. Boom, boom. Now it's eclipsed. Right? There you go. Carbon 1 doesn't change. Rotate carbon 2 again clockwise. There's 1 and 2. Again, carbon 1 did not change. And now we're back to staggered. And the carbon 1 has an H below. Carbon 2 has an H up top. So that's that staggered conformation. So this, we wanted you to draw a new projection of D as wedged and dashed structure. So how could you do that? So 1 and 2. So we know it's a clip, or do we know it's staggered? So 1 H is down, 1 H is up. Bromine is on my left-hand side with CH3. So they're both dashed. CH3 in the front, right there. Cl right there. On the right, so they're wedged. Below, match your reactions as addition, substitution, elimination, or proton transfer. Elimination here because we're making a pi bond. Proton transfer because an H is moving. This oxygen is grabbing that H. This is a proton transfer. Substitution, a bromine is being substituted for a nitrogen piece. And then addition, because you're losing a pi bond, you have a pi bond, and then you lost one of the pi bonds, you're adding things across it, so that's an addition reaction. Draw the mechanism areas on the starting materials to form the product. So on the starting materials to the left. All right, so we got to look here. What happened? Looks like a new NH bond was formed. So we draw in our lone pairs. You should draw lone pairs in first. Arrows start at lone pairs. Grab the H. Look at the electrons between the N and the H go to the nitrogen. End up there. So those are 2 arrows. Make sure you know where arrows start. Arrows should start at a lone pair, a pi bond, or any time of that. Be careful with that. The products are favored because the lone pair in sp hybrid orbital. So this nitrogen's sp hybridized. That lone pair is in sp hybrid orbital, which is shorter and closer to the nucleus. So that makes this side more stable, less reactive. This is in an sp3 hybrid orbital, which is longer, farther from the nucleus, so more reactive. That makes it more likely to go this direction. Here, oxygen. Does it have any pi bonds? No. Does it have lone pairs? Yes. Is it one bond away from another p orbital? No, so it's sp3 hybridized. Does it have any pi bonds? No. Does it have any lone pairs? No. sp3 hybridized. Does it have any pi bonds? Yes, it has 2. sp hybridized. So make sure we understand those hybridization states. Now moving on to some of these ring flips. Understanding chairs. So you start here. Number your atoms. Doesn't matter how you numbered them. I just numbered them this way. We can go this way first. If I number this 1, I like to think of down as dashed. So dashed is down. This 3 carbon piece is up, wedged. And this NH2 is also wedged, right? Number your carbons, make sure you get in the right spot. So number it here and number it here. Doing a ring flip, what would happen is 1 gets pulled up, 4 gets pulled down. So 1's up, 4 is down. If you were down, you always stay down, but this was axial. So now instead of being axial, it's going to be down and equatorial. This was up and axial, so now it's going to be up and equatorial. And the nitrogen was up and equatorial, so now it's going to be up and axial. So those are the right positions. Make sure you number your atoms. That's the best way to keep track of things. Remember, I always like to think of things down as dashed. It just helps me remember it. And if things were axial on the ring flip, they become equatorial. But if they're down, they always stay down, and vice versa. Some resonance. I want you to add lone pairs to each structure. So one of the things people forget, there should be lone pairs on the carbanions, the negatively charged carbon. Draw the lone pairs in on the oxygens and on the nitrogens. So draw those lone pairs in on each structure. This first one, it looks like electrons end up on this carbon, so they have to move from the oxygen to make a new pi bond. Pi bond breaks, ends up on the atom. So there's a lone pair there. Electrons move, make a new pi bond. Electrons from that pi bond end up on this carbon. They keep moving, make another pi bond, break a pi bond. So the nitrogen has 2 lone pairs. Now to bring it all the way back, we're going to have to do a couple arrows. Electrons move there to make a pi bond. Another pi bond needs a break to make a new pi bond. Pi bond needs a break to make a new pi bond. Pi bond needs a break and finally end up on the atom. So this is 4 arrows, but it's just adding all these steps together essentially. So think about bonds, broken bonds formed, where your arrows should start, in which direction they should flow. Right? They should flow, right? If there is a negative charge ending up over here, the electrons need to flow to that spot. That's what they need to end up at. Electrons here, negative charge, they start here and they end up towards the positive charge because that's where the lone pair ends up. So all in one step. So keep track of bonds, broken bonds formed. Make sure you start arrows at electrons. Make sure you draw arrows between atoms for pi bonds and end. If you need to end a pi bond, add an atom, make sure you do that. And don't forget to add electrons for the carbanions, for the carbons with a negative charge. Lone pairs there. Some rankings. For this one, we'll do the first one. Carbon, 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 carbon is all a tie. This one is bound to 3 hydrogens, so I can draw these in let's see. So it'd be H, 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 C, H, H, C, C, H, and C, C, C. So this would be the lowest ranked. Hydrogen loses carbon, so that's green. Highest ranked would be this one because carbon, 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 that's a tie. Right? So these guys all tie. They tie, they tie. And then carbon beats this one, so this is the blue, lowest third ranked. And carbon, carbon, still tied. Carbon beats hydrogen, so this is red. Once you do that, then you should have it, the rankings correct, and you use your model to make sure that this is an S, right? You grab the green ball, turn it towards you, red, white, blue. So it's counterclockwise. Same thing down here. Big thing folks messed up, they looked at electronegativity instead of atomic number. Sulfur has the highest atomic number. Then fluorine, then oxygen, then nitrogen. So once you do that, it should be R, but make sure you do it by atomic number, not by electronegativity. All right, last bit here. Got a ring. All these are pointed up. Oh, they're all be pointed down. So I drew them all pointed up. So as you can see, I didn't number here. I should have. 1, 2, 3, 4, 5, 6. I like to think of the wedge is going up. So OH is up axial, CH3 up equatorial, NH2 up axial. O and the methyl, don't forget the carbon on here, is up equatorial. Make sure you copy those things correctly. Numbering atoms again is key. Last thing, draw some resonance arrows here. So this arrow breaks, that's forming a new pi bond. This atom lost a bond, so now it has the plus charge, has electrons. And then to get to here, you need to move an arrow there, make a pi bond, there, make a pi bond. Now the oxygen has a plus charge, so make sure you draw these things correctly. Again, numbering atoms would be a good thing to do. Major resonance form is C, because everyone has a full octet, whereas these are carbocations, they don't have full octets. So even though the oxygen has a plus charge, this is more stable because everyone has a full octet, and that's the first thing we want to think about.